Alright, one more problem just for the fun of it. So this is problem 79 on page 133. This one has a star, so it's a little more challenging. Oops. Okay. So this one says you can consult multiple concept example 10 for insight into solving this type of problem. So that's a hint. If you're stuck, that's where you should go for help. Alright, so this says a box is sliding up an incline that makes an angle of 15 degrees with respect to the horizontal. So I've drawn that, I've started that here on the screen. The coefficient of kinetic friction between the box and the surface of the incline is 0.180. So we can record that. Mu k equals 0.180. Alright, it also says the initial speed of the box at the bottom of the incline is 1.50 meters per second. So we also know V naught. The question says, how far does the box travel along the incline before coming to rest? So we're looking for x, the distance traveled. Another clue there, there's not a number, but it says before coming to rest. So that tells us something about the final velocity. That means the final velocity is going to be 0. So we have the beginnings of some kinematics information here. If we wanted to use one of our kinematics equations, the one thing that's in all of the equations that you have to know is the acceleration. We don't know that. However, we do know that acceleration is linked to forces, and we can figure out something about the forces on the incline. So let's look at the forces acting on the incline. We have gravity that points straight down. It's our Fg. We have the normal force that points out like this, perpendicular. And then we have friction. So this is a little bit tricky here. The problem said that the box is sliding up the incline. So in other words, it was sliding along, or somebody gave it an initial push, and now it's sliding up the incline because of its momentum. So friction must be acting down the incline because it always acts in the opposite direction of the motion. So FFK points down the incline, and there's no force pushing up the incline. Nothing is continuing to push on this, it just was initially moving that way. So it's going to slide that way for a little bit. So looking at this, we should be able to tell that this box is going to be slowing down. And from the question, that was implied because it said it's going to come to rest at some point on the slope, and we're finding how far up the slope that is. Alright, so we need to focus on finding the acceleration. Let's do that in a different color. Alright, we know that the net force is related to acceleration by F net equals ma. So we're only interested, we know the acceleration is going to be along the incline. It's not going down into the slope or up off the slope. So the net force is going to be the forces along the x direction. So that's going to be FFK and FGX, or FG sine of 15 degrees. Alright, so now, before we start putting in the net force, it may be a good idea to define our coordinate system. So let's say that the direction of motion is positive. That would make the opposite direction negative. So according to that coordinate system, FFK is negative. So we have a negative value for FFK, and then we also have FG sine theta, or sine theta, in this case 15 degrees. That's going to be negative also. We don't have any forces pushing in the positive direction, so it's just those two equals mass times acceleration. Now, we were not given the mass in the problem, so we're going to have to find some way to cancel out this mass. So let's try expanding these things. We can put FFK in terms of mu k times the normal force. So let's factor out this negative first. And we'll call this mu k times Fn. And then since we factored out the negative, that becomes a plus. And we can expand this. Fg can become m times a little g times sine of 15 degrees. So all that equals ma. Now, we're a little closer. We have an m here. We need to get this in terms of m. So we need to expand the normal force. What is the normal force? That's just going to be equal to our y component of the force of gravity. That has to be balanced by something so that the box isn't raising up off the incline. So that's balanced by Fg cosine of 15 degrees. So now we can write this as mu k times, and Fg is just m times g times cosine of 15 degrees plus m times g times sine of 15 degrees equals ma. Now we have an m in each term here, so we can divide everything by m and cancel out all of our m's. That's good because we didn't know m. So now if we wanted to simplify this a little bit, we could factor out a g in front. So this becomes negative g times mu k times cosine 15 degrees plus sine 15 degrees. And that equals a. So then plugging in our known values, we get a equals negative 4.24 meters per second squared. So that's not our answer. What we were asked to find is how far up the slope does it go. So now we can go back up and look at our kinematic stuff. And now we know a is negative 4.24 meters per second squared. So does this value make sense? Well, this negative means that the acceleration points down the incline. That's the same as the direction of the net force, and that's opposite the direction that it's moving. So that means it's going to slow down as it moves forward. So that makes sense. So now we need an equation that hopefully has all of these things in it without having time in it, because we don't know the time. So we do have an equation like that. It's this one. V squared equals V naught squared plus 2a times x minus x naught. So v squared is 0. That's easy. V naught is 1.50 meters per second, and that whole thing gets squared, plus 2 times our negative 4.24 meters per second squared times x. So x naught is 0. We can just set the initial position as 0, so then we don't need to worry about that. So solving for x, that gives us x equals 0.265 meters. And that is the answer to the question.